Hi everybody, sorry I can't make it today, but I do want to go on with our curriculum. And so today we're going to be going over radiometric dating, and this is something you guys have already heard about because you read about it a little bit in chapter 16, and you guys have already turned in your infographics, hopefully, and you guys have read about a lot of different dates and a lot of different organisms that existed in your time period, and it might get you wondering, like, how do they know all this stuff happened? It's not like we have a video of the Cretaceous period to play. So everything scientists know about those periods come from fossils and fossil data and rock layers and dating the rocks and seeing how old the rocks are around them. And so all that is done by radiometric dating. So this is an archaeological dig right here, and they're finding these fossils, and it really means nothing if we don't know how long they've been there. Okay, so to date an actual fossil, a piece of a living organism, like a bone, for example, we're going to use carbon dating. And so you guys remember from our first unit, carbon is really important to living things. It makes up the backbone of most of the molecules that are in our body. So carbon enters our body as CO2, as carbon dioxide, okay? So this dinosaur, when it was alive, was breathing in carbon dioxide. Now, C12 is the normal type of carbon dioxide, no big deal. But we know that some carbon atoms are a little bit heavier in the atmosphere. Okay, so let me show you how they get heavy. So basically, radiation from the sun is going to hit nitrogen. Nitrogen is really, most of our atmosphere is made up of nitrogen molecules. And what's going to happen, it's going to knock off neutrons off of nitrogen, and some of those are going to be captured by the carbon, okay? So instead of having the regular number of neutrons, this carbon atom is going to be heavier, and it's going to have extra neutrons. Okay, now when it absorbs these extra neutrons, it's very unstable. It's going to want to get rid of those neutrons, and every time it does get rid of neutrons, some energy is going to be released. All right, but let's go back. So some of the carbon dioxide is actually going to be this carbon-14, so the special radioactive form of carbon, okay? And so some of it's going to be normal CO2 going in, some of it's going to be heavy carbon-14 CO2 going in. So pieces of its body are going to be composed of a heavier form of carbon. Now this is going on in our own bodies as well. So you might be thinking, we have radiation in our own bodies? Very low levels we do. Yeah, and when the dinosaur dies, it's not going to be breathing in any more carbon dioxide, right? So whatever amount of heavy carbon it took in during its lifetime is going to still be there. And we know that most organisms are breathing in about the same amount of CO2, depending on their size. So they're going to have a certain level of radioactivity in their body, okay? So we can measure that radioactivity with machines and figure out how old the fossil was. So if we can't quite date the actual living or formerly living tissue, we can date the rocks around it. So we don't have to use carbon. Sometimes we may measure uranium. Okay, so uranium's actually very highly unstable, so this isn't a great example, but I like this picture because it shows that these uranium atoms are turning into iron. So they are shedding their extra particles. And remember, when it gets rid of extra particles like neutrons, it's going to also give off radiation. Okay, and you see that after 1 billion years, only half of the uranium is there. Okay, so this rock is going to have half of the radiation of the original rock. And so however long that takes for half of them to turn, that's called the half-life. Okay, so the half-life, you can say, of uranium is 1 billion years. Okay, so if we find a rock that's 2 billion years old, this is how much radiation you should see. There's only a few uranium atoms left here, so it won't be giving off very much radiation at all. Okay, so you can see another billion years, half of those have decayed and turned back into iron. All right, so we know that this whole decay thing and getting rid of the extra particles, it happens at a very set rate. And so that rate we can see, and so it helps us date the fossils, okay? So let's go back here and just review really quick. Let's say this is carbon-14. It's radioactive. Remember, it's 14, so it's a little heavier than the normal 12. And it's going to get rid of the extra neutron. Okay, and in the process, radiation is released. And this whole process is called radioactive decay. Okay, so this uranium is decaying, and the half-life is the time for half of the sample to decay. Okay, so a lot of times you'll get these graphs like this. So this shows the percentage of carbon-14 remaining. So at the beginning, so this is death here, there's going to be 100% of the carbon-14 that organism breathed in. Over time, though, remember, the carbon-14 is going to release its extra particles and release the radiation, and those levels are going to decline because all the carbon-14 is going to go back to normal carbon-12. And so you'll see a decrease in radiation over time. All right, now you can see that it goes from 100 down to 50%, okay? It gets cut in half in roughly 6,000 years, okay? So this is the half-life for carbon-14, okay? So if you get asked what is the half-life, you start from 100% or whatever the number is, go down to half, and figure out how long it took, okay? So I just came across here and figured out how long that was. Okay, so let's say we found a fossil, we found a piece of bone, a piece of whatever, and we found that it, let's say it had 30% of its carbon, okay, remaining. So we wanted to know how old is it? So we put it in a machine, and the machine says there's about 30% of its radioactivity remaining. So you go over and you see, okay, that's about, let's see, maybe 9,000 years old, okay? Sometimes you have to estimate these based on the graph, so do your best. Okay, so if a sample was 9,000 years old, we would know that it had about 30% of its carbon-14 isotopes remaining. Okay, isotopes, that's another term you'll hear. So let's go back to this picture. Anything that's radioactive, anything that's not the normal weight for an atom is called an isotope. So this is the carbon-14 isotope. Okay, so it's different from the regular atom because it's heavier. Okay, so anytime we find a fossil, again, we're going to put it, this is a Geiger counter, and so we put that near the fossil, and it tells us how much radioactivity there is. And once we know how much radioactivity there is, we just look at the y-axis of a decay graph, and we go across and see what that corresponds to. Okay, and so you should at this point be able to work on the worksheet that the sub is going to pass out. Good luck, and I'll check those off for completion when I get back, and then I'll give you guys the solutions, okay? Good luck.